far beyond our world, in the constellation of Leo, nearly 120 light-years from Earth. A telescope has captured something that could transform everything we thought we knew about life in the universe. The James Webb Space Telescope has found a planet where the climate remains steady at 120 degrees Fahrenheit. Cloaked in an atmosphere echoing with the chemical fingerprints of living creatures, scientists are 99.7% certain. This may be a planet teeming with life, a world perhaps even more habitable than Earth itself. Like and subscribe as we journey to witness humanity's greatest discovery. Prepare yourselves. The story begins the day it arrived quietly on a Tuesday morning in December. Hidden within terabytes of infrared signals captured by humanity's most powerful eye in space was a revelation waiting to be uncovered. At Cambridge University, Niku Meduzin stared at the streams of data, light that had traveled across 120 light-years to finally reach Earth, and then he froze. In the spectrum of an alien atmosphere was a signature that should not have been there. Dimethyl sulfide. On Earth, only life produces this molecule. Here, it wasn't just a trace, it was a clear, undeniable signal. The chance of error? Less than 3 in 1,000. The James Webb Space Telescope had revealed what every astronomer had only dared to dream of. Direct evidence of life beyond our solar system, the world. Designated K218b circles a red dwarf star in the habitable zone, a region where liquid water can exist. But unlike anything in our solar system, this planet is a giant, more than 8 times the mass of Earth, wrapped in a hydrogen-rich atmosphere that works like a perfect greenhouse. Beneath alien skies, vast oceans may spread endlessly, their waters remaining liquid thanks to the steady warmth. Temperature readings were astonishing, 120 degrees Fahrenheit, a balance so precise, warm enough for life to thrive, yet cool enough to prevent oceans from evaporating. For months, Meduzin's team had tracked the planet's every transit, each pass across its star revealing another clue. First came water vapor, then methane, then carbon dioxide. And finally, the turning point, dimethyl sulfide. This one molecule, so closely tied to biological activity, was like a neon sign blazing in the cosmic dark. For Meduzin, the realization hit like a physical force. If true, humanity's loneliness in the cosmos was over. The probability was staggering, 99.7% certainty. In astronomy, a field where doubt is common and many discoveries crumble under scrutiny, this level of confidence was almost unheard of. In K218b wasn't just any world. Its unusual traits suggested it might be even more welcoming to life than Earth itself. Its thick hydrogen atmosphere acts like a global blanket, spreading warmth evenly, creating stable conditions across the entire surface. Unlike Earth's thin nitrogen skies that allow extremes, this alien planet could be home to vast, enduring oceans and perhaps the life that stirs within them. The Stark 218, the star at the heart of this discovery, is no ordinary sun. It is a red dwarf smaller and cooler than our own star, yet astonishingly stable. While our sun will one day swell into a red giant and erase all life on Earth, red dwarfs burn slowly, shining with steady energy for trillions of years. For any life clinging to a planet like K218b, this means vast stretches of time to evolve and grow into forms beyond anything we can imagine. As Niku Meduzin prepared to share his findings with the world, he understood that December morning would be remembered forever, the moment humanity discovered it was not alone. But this was only the beginning of a story destined to reshape everything we thought we knew about life, the universe, and our place in it. For decades, scientists assumed that if we were to find life, it would be on a planet just like Earth. Rocky, orbiting a sun-like star with the right balance for liquid water. K218b shattered that belief. This strange world proved life could thrive under conditions so alien we had never even thought to search there. A super-Earth K218b belongs to a class of planets called super-Earths, worlds larger than Earth but smaller than Neptune. For years, astronomers dismissed them as nothing more than bloated gas spheres, too massive and too hostile to sustain life. But this discovery forced scientists to completely reimagine what a habitable planet might be. its immense size creates surface gravity nearly 3 times stronger than Earth's. Someone weighing 150 pounds here would weigh over 400 pounds on K218b, but this crushing pull might actually help life. The powerful gravity locks the atmosphere in place, preventing it from bleeding away into space. The same fate that stripped Mars of its air billions of years ago, even the atmosphere itself, defies all expectations. Unlike Earth, dominated by nitrogen and oxygen, K218b skies are overwhelmingly composed of hydrogen and helium. On Earth, hydrogen is almost non-existent, less than 1 part per million. But here, it makes up the vast majority of the atmosphere, creating an environment utterly alien to our own. This thick hydrogen cloak doesn't cook the planet, the way Venus is scorched by carbon dioxide. Instead, it acts as a perfect insulator, spreading warmth evenly across the globe. Even the planet's dark side, locked away from starlight, remains warm enough to keep oceans liquid. The signs of life the James Webb Space Telescope revealed more than just hydrogen. Alongside the life-indicating dimethyl sulfide, its instruments detected methane, carbon dioxide, and water vapor, a chemical cocktail that points to active biological processes on Earth. This same mixture is produced by everything, from microbes to complex ecosystems, creating a planetary metabolism visible even from space. But perhaps most striking was what wasn't there: ammonia. If K218b were a sterile gas giant, ammonia would dominate its atmosphere. Its absence suggests something extraordinary: life is actively removing it. This meant one thing: life on K218b is not a passive presence. It is shaping the planet's atmosphere, rewriting its chemistry. Just as life on Earth transformed our skies with oxygen billions of years ago, a universe reimagined, the implications are staggering. If life can emerge and thrive in the hydrogen-rich skies of a super-Earth, then the number of potentially habitable planets in our galaxy may be hundreds of times greater than we ever believed. Red dwarfs like K218, which make up nearly 3/4 of all stars in the Milky Way, suddenly become the prime hunting grounds for extraterrestrial life. We may not need to search for Earth's twin after all. Instead, we may find Earth's strange cousins' worlds thriving in conditions we are only just beginning to understand. The machine that made it possible, and at the center of this revolution is the James Webb Space Telescope itself. Not just a tool, but a time machine, gazing deeper into the cosmos than any instrument ever built. Stationed 1,000,000 miles from Earth at the gravitational balance point known as L2, Webb drifts in eternal darkness. Its giant sunshield blocks the glare of our star, keeping its instruments colder than the surface of Pluto, its primary mirror a gleaming golden eye 21 feet across, nearly 3 times larger than Hubble's pushes astronomy into a new era, made from 18 hexagonal segments, each coated with an ultrathin layer of gold. The mirror reflects faint traces of infrared light with unimaginable precision. Aligned together, they form an eye so sensitive it could detect the heat signature of a bumblebee on the moon. Infrared light, invisible to human eyes, holds the key to unlocking the atmospheres of distant worlds and perhaps to finding life itself. Coronagraph technology: when a planet drifts across the face of its star, a small fraction of starlight filters through its atmosphere before reaching Earth. Hidden within that light are chemical fingerprints, unique patterns where molecules absorb specific wavelengths of infrared radiation. The James Webb Space Telescope can detect these patterns with a sensitivity that borders on the impossible. To understand the challenge, imagine trying to spot the glow of a firefly hovering beside a blinding searchlight from 1,000 miles away. The star K218 is billions of times brighter than the planet orbiting it. Yet Webb can separate the faint infrared glow of the planet's atmosphere from the overwhelming brilliance of its star. Webb's secret weapon is its coronagraph technology. Originally developed to block out starlight and reveal hidden worlds, it uses advanced image processing to strip away the glare. What remains is the delicate signature of atmospheric molecules, like muting the roar of a jet engine until the faintest whisper can be heard beneath it. At the edge of possibility. The detection of dimethyl sulfide on K218b pushed Webb to its very limits. The molecule produces an infrared signal so faint that it required repeated observations stretched over months. Each pass captured only a handful of photons, particles of light that had crossed 120 light-years of emptiness, carrying within them the story of life on another world. And Webb delivered. The telescope didn't just reveal chemical signatures. It also measured the planet's temperature with astonishing precision, a steady 120 degrees Fahrenheit, warm enough to keep vast oceans liquid, yet cool enough to prevent them from vanishing into space. This was no rough estimate. Webb determined it within just a few degrees across interstellar distances. It is one of the most precise measurements ever made of an exoplanet's environment. The power of algorithms extracting these discoveries from raw, infrared data is a challenge as great as building the telescope itself. The signals are faint, buried in noise and scattered across millions of data points. To solve this, astronomers turn to some of the most advanced algorithms ever created. Artificial intelligence now combs through Webb's data, searching for subtle patterns no human eye could ever detect. It identifies the molecular fingerprints of distant worlds, teasing out order from chaos, and revealing the chemical stories hidden in starlight. A new era, the discovery of life on K218b, is more than an engineering triumph. It is proof of what humanity can achieve when it pushes against the edge of possibility. The James Webb Space Telescope has not only opened a new chapter in astronomy, it has changed our relationship with the cosmos itself. We are no longer asking if life exists beyond Earth. We are beginning to glimpse where temperature we are watching it breathe, 120 degrees Fahrenheit, a number so precise it feels almost unreal. The heat of a scorching day in Death Valley, the warmth of a hot spring, the fevered burn of a human body fighting infection, and on K218b, it is the temperature that sustains an entire planet's possibility for life. Temperature is everything. Too cold and water freezes into solid ice, halting the chemical reactions needed for life. Too hot and water evaporates into vapor, leaving only barren landscapes. Life can only exist in the fragile space between. Astronomers call this narrow window the habitable zone. Earth is lucky enough to sit almost exactly in the middle of it, a cosmic accident that allowed life to flourish here for billions of years. But on K218b, this balance is no accident. Its perfect 120 degrees Fahrenheit climate is the product of a delicate harmony between its star's energy and its atmosphere's chemistry, creating conditions more stable than anything found on Earth, a cosmic balance orbiting its red dwarf star. K218b receives nearly the same amount of energy per square meter as Earth does from our Sun. It is a cosmic coincidence that places it in a thermal environment almost identical to our own world. Despite being 120 light-years away, the secret lies in its atmosphere. Unlike Earth's thin veil of nitrogen and oxygen, which allows heat to escape rapidly, K218b is wrapped in a dense blanket of hydrogen. This cloak traps infrared radiation, producing a greenhouse effect that distributes heat evenly across the planet. Even the side of K218b, locked in eternal night, never touched by starlight, remains warm enough to sustain liquid oceans. A world without seasons. On Earth, life is shaped by change. Day and night, summer and winter. Shifting seasons force organisms to adapt, to migrate, to hibernate, to evolve strategies for survival. But on K218b, stability reigns. Its thick hydrogen atmosphere redistributes heat so efficiently that every region of the planet maintains nearly the same life-friendly temperature. For life here, survival would not mean enduring extremes. It would mean thriving in stability. Energy could be spent not on defense against the environment, but on growth, reproduction, and evolution. The sweet spot for life most astonishing of all. K218b's steady 120 degrees Fahrenheit is not just survivable, it may be ideal. Laboratory studies on Earth show that biological processes remain efficient at temperatures up to 250 degrees Fahrenheit. At 120 degrees Fahrenheit, Chemical reactions move quickly enough to fuel complex metabolisms, yet remain cool enough to protect delicate molecules. From breaking down, it is not just habitable. It is welcoming, more than an accident in a universe dominated by frozen wastelands and blistering infernos. K218b is something extraordinary, a planet in perfect thermal balance. Here, life would not simply endure. It would flourish. Dimethyl sulfide? The name may sound like a chemical tongue twister, but behind these three words lies perhaps the most important discovery in human history. When the James Webb Space Telescope detected dimethyl sulfide in the skies of K218b, it uncovered something no non-living process has ever produced. It uncovered the signature of life itself. On Earth, this molecule is created only by living organisms. Tiny phytoplankton in our oceans generated as a byproduct of their metabolism, releasing it into the atmosphere where it even helps shape clouds and influence weather. Marine bacteria, algae, and certain plants also produce it as part of their natural cycles. But here's the critical detail. No geological or chemical process, no lifeless system, has ever been observed producing dimethyl sulfide. That is why its detection on K218b is revolutionary. Scientists classify it as a biosignature, a molecule that can only exist when life is present. Unlike oxygen, which can also form through non-biological processes, or methane, which can seep out from rocks, dimethyl sulfide has no known abiotic source. Its presence in an alien atmosphere is as close to proof of life as science can currently achieve without directly seeing the organisms themselves. The chemistry of life. The molecule itself tells a deeper story. Dimethyl sulfide is made of sulfur. Atoms bonded to carbon-based methyl groups, a chemical structure so specific it requires specialized enzymes to form. On Earth, these enzymes are the product of billions of years of biological evolution, part of the sulfur cycle that regulates our planet's atmospheric chemistry. The fact that similar molecules appear on K218b suggests something extraordinary. Life there has also evolved sophisticated biochemical pathways. Not just chemistry, biology. But perhaps the most astonishing revelation wasn't the presence of dimethyl sulfide. It was its abundance, a thriving biosphere. The concentrations of dimethyl sulfide detected by Webb were far too high to come from a young or struggling biosphere. Instead, they suggest an ecosystem operating on a planetary scale. This is not the faint whisper of microbes surviving in scattered niches. This is a chorus life so vast and productive that it is actively reshaping the chemistry of an entire world's atmosphere. If a molecule like dimethyl sulfide can be detected from 120 light-years away, the biosphere responsible must be immense. Oceans alive with plankton-like organisms, skies filled with the chemical exhalations of countless life forms, a planet not just alive but thriving, the universal code of life. This discovery raises profound questions. If organisms on K218b are producing dimethyl sulfide, they must have evolved pathways eerily similar to those on Earth. This hints at a startling possibility. The fundamental chemistry of life may be universal. Carbon, hydrogen, oxygen, nitrogen, sulfur, the same building blocks repeating across worlds, assembling into complex molecules again and again wherever conditions allow. Life may not only be common in the universe. It may follow the same predictable patterns, written into the fabric of chemistry itself. Not alone, the detection of dimethyl sulfide is more than a scientific achievement. It marks a turning point in human history. This is the moment we learned, with clarity and certainty, that we are not alone somewhere under alien skies, somewhere 120 light-years away, under alien skies rich with hydrogen. Life is breathing, growing, and transforming the chemistry of an entire world for the first time. In human history, we now hold evidence that life exists beyond Earth. In science, certainty is rare. Scientists usually speak in probabilities, confidence levels, and margins of error. They hedge their conclusions, weigh alternative explanations, and acknowledge doubt. But when James Webb Space Telescope data from K218b was analyzed, the numbers were undeniable. The results revealed a 99.7% probability that the dimethyl sulfide signal was real. Asterisk. The weight of certainty. What does 99.7% really mean? Imagine flipping a coin 1,000 times. Getting heads or tails on any single flip is equally likely. But the probability of flipping heads 997 times out of 1,000 is so impossibly small, it would never occur by chance in the entire history of the universe. That's the level of confidence scientists now have that the signal of dimethyl sulfide. Life's chemical fingerprint on K218b is authentic. Sigma detection. This level of certainty comes from a technique called sigma detection, a statistical framework used in both particle physics and astronomy. 3 sigma detection corresponds to a 99.7% probability that a signal is real, only 3 in 10,000 times. Would such a signal be a false alarm? This is the same threshold that confirmed the existence of new subatomic particles, verified gravitational waves, and validated some of the most profound scientific discoveries of the modern era. And now, it has been reached for the detection of life beyond Earth, unprecedented precision, but reaching this confidence for a planet 120 light-years away demanded technology of unimaginable precision. The dimethyl sulfide signal was incredibly faint, measured in just parts per billion within the infrared spectrum. To detect it, Webb had to measure wavelengths of light to an accuracy of 1 part in 10 million. That's like measuring the width of a human hair with the precision of a single atom. Multiple independent observations, spread across months, confirmed the signal again and again. Webb's instruments picked out the same molecular fingerprint at different wavelengths, providing redundant proof. Meanwhile, advanced computer algorithms processed millions of data points, searching for errors, contamination, or artifacts that might mimic the signal. None were found. Every alternative hypothesis, unknown chemistry, Earth-based contamination, or instrumental error was tested and eliminated. The only explanation left standing was this biological production of dimethyl sulfide. A quantum leap. This level of certainty is almost unheard of in exoplanet science. Most atmospheric detections on distant worlds barely meet the threshold for journal publication. But the 99.7% confidence level for K218b represents a quantum leap in our ability to identify life. The implications are staggering. When scientists say they are 99.7% certain life exists on K218b, they are making a statement as reliable as the structure of DNA, as solid as Einstein's theory of relativity, and as established as the age of the universe itself. Beyond wonder. We are no longer left asking the ancient question, does life exist elsewhere? Now we know. Life does not belong to Earth alone. The hydrogen ocean beneath the alien skies of K218b lies an ocean unlike anything in our solar system. It is not simply water, but a vast sea of water mixed with hydrogen, an environment so exotic that no Earth-based life form could survive its crushing pressures. And yet, paradoxically, this alien ocean may be the most life-friendly environment in the known universe. This ocean exists because of K218b's unique chemistry. Its hydrogen-rich atmosphere does not merely float above the surface, it dissolves into the liquid water itself. The result is a stable solution that can remain liquid across a staggering range of conditions, from just above freezing to over 300 degrees Fahrenheit, for life. This means an enormous window of opportunity in which to thrive. On Earth, the deepest trenches of our oceans exert pressures 1,000 times greater than at sea level, enough to crush most life forms. But on K218b, hydrogen acts as a natural pressure buffer, softening the extremes. Even in the planet's deepest reaches, the hydrogen solution maintains water-like properties at relatively moderate pressures. *A reservoir of atmosphere. This hydrogen ocean does more than provide a home for life. It may ensure the planet's very survival. On Earth, our atmosphere is slowly bleeding away into space, a process that will one day leave our world barren, like Mars. But on K218b, the ocean acts as a massive atmospheric reservoir. As hydrogen escapes into space, more hydrogen seeps out of the ocean to replace it. The cycle could sustain a stable, life-supporting atmosphere not for billions, but for trillions of years. This means life on K218b may have an unimaginably long timeline to evolve, adapt, and flourish far longer than life on Earth ever will. Breathing. The ocean. The chemistry of this ocean opens doors to forms of life that Earth has never known. Here, hydrogen itself becomes an energy source. On Earth, a few rare bacteria metabolize hydrogen, but they struggle because of its scarcity. On K218b, hydrogen is everywhere. Organisms could literally breathe the ocean, thriving in an environment where their primary energy supply is inexhaustible. Even more astonishing, such life might be invisible to our traditional detection methods. Our searches focus on oxygen, on photosynthesis, on signatures familiar from Earth, but in K218b's hydrogen ocean, organisms could metabolize in ways utterly alien to us. The dimethyl sulfide detected by Webb might be only the beginning, a single clue among countless unknown biosignatures hidden in this alien sea. An ocean without end. The true depth of this hydrogen ocean is still a mystery. Models suggest it could plunge hundreds of miles below the surface, far deeper than Earth's oceans. Imagine a vast, dark volume of liquid water and hydrogen, stretching beyond human comprehension. Within it, ecosystems of unimaginable complexity could thrive, evolving along paths so foreign that we can scarcely begin to imagine them. This is more than habitability. It is a fundamental shift in what it means for a world to be alive. Atmospheric chemistry. Above this alien ocean stretches an atmosphere that feels like science fiction brought to life, where Earth's air is a simple mix of nitrogen and oxygen. K218b's skies are a swirling cosmic cocktail of molecules. Methane drifting through hydrogen clouds. Carbon dioxide crystallizing into ice-like forms in the upper layers, and deeper still, under crushing pressures, carbon atoms compressing into sheets of diamond rain. Even the methane itself tells a story. On Earth, methane is produced by life from microbes in swamps to the digestive systems of animals, but it doesn't last. It breaks down in decades. The fact that Webb detected large amounts of methane on K218b means that something is actively replenishing it, potentially in vast, continuous cycles. In this hydrogen-rich world, methane does more than betray the presence of life. It also acts as a crucial regulator in the planet's carbon cycle, helping balance its climate and stabilize its alien atmosphere. Beyond Earth, the discovery of K218b's hydrogen ocean and atmospheric chemistry forces us to expand our imagination. We are no longer just searching for Earth-like worlds. We are searching for worlds that may be better than Earth. In the hydrogen seas of super-Earths orbiting red dwarfs, life might not just endure, it might flourish in ways that make our own biosphere seem limited by comparison. The universe's most life-friendly environments may not resemble Earth at all. Instead, they may be the most alien places we can imagine. Organisms on K218b. On K218b, life would not play by Earth's rules. Here, organisms might actually breathe methane, metabolizing it as a source of energy in ways utterly impossible on our world. To us, such a process feels alien, even magical. But on this planet, it could be the very foundation of survival. Above their oceans, the skies themselves transform into a spectacle of strangeness. At certain altitudes, the immense pressure and temperature combine to force carbon atoms into diamond crystals. These microscopic diamonds form high in the atmosphere and then drift downward in a glittering storm. For us, a miracle. For them, just weather. On K218b, diamonds fall as casually as raindrops. Alien chemistry, but the strangeness does not end with diamonds. The atmosphere of K218b contains abundant carbon dioxide, far more than Earth's thin trace amounts. Here, CO interacts with hydrogen and methane in a three-way chemical dance, creating an environment capable of supporting entirely new forms of photosynthesis. Imagine alien organisms, not using sunlight and water in the way Earth's plants do, but instead tapping into a chemistry built from hydrogen, Methane and carbon dioxide, a photosynthesis unlike anything in our biosphere. Atmospheric dynamics. Driving this alien chemistry is the planet's most dramatic feature, its locked rotation. One hemisphere of K218b forever faces the red dwarf star, locked in eternal daylight, while the opposite side lies in unending night. This creates massive atmospheric rivers of gas and energy, transporting heat, moisture, and chemicals across the planet. Instead of one world split in two, the circulation transforms it into a balanced, living system where chemistry and climate remain surprisingly stable. Even more remarkable, the thick hydrogen atmosphere serves as a planetary shield. Red dwarfs, like K218, are notorious for violent solar flares, powerful bursts of radiation that could sterilize an exposed surface. But here, the atmosphere itself absorbs and deflects much of that radiation, protecting the surface below. This natural defense could be what allows complex ecosystems to survive and evolve in the first place. Diamonds. Methane and evolution. In such an environment, life would not only adapt, it might surpass Earth in sophistication. Consider it. Ecosystems shaped by methane-breathing organisms, thriving beneath skies where diamonds reign, in an atmosphere that shields against lethal radiation, fueled by chemical cycles beyond Earth's imagination. The biosignatures that the James Webb Space Telescope has already glimpsed, molecules like dimethyl sulfide, might only be the first hints of a biochemical story far richer than ours. The red dwarf star. At the heart of this alien world is its star K218, a red dwarf, unlike our sun, which will one day swell into a red giant and erase all life on Earth. Red dwarfs are cosmic survivors. They burn cool, dim, and steady, with lifespans measured not in billions, but in trillions of years. For life, that means stability beyond imagination. While Earth's biosphere is bound to perish, worlds around red dwarfs like K218 may enjoy a near-eternal spring, with energy supplies lasting long enough for life to evolve into forms beyond anything we can conceive. And red dwarfs are not rare. They are the most common stars in the universe, making up nearly 3/4 of all stars in our galaxy. This means that planets like K218b may not be the exception. They may be the rule. Complex life. Red dwarfs may be small, often less than half the mass of our sun, but their slow-burning nuclear hearts make them the most enduring stars in the cosmos. While our sun will shine for only about 10 billion years, stars like K218 can continue glowing for up to 10 trillion years. That's 1,000 times longer than Earth's entire history. On our world, it took nearly 4 billion years for life to crawl from simple microbes to the dazzling diversity of ecosystems we know today. Now imagine life on K218b, nurtured under the steady flame of a star that could outlast galaxies themselves. If life has even a fraction of that time, it might not just equal Earth's complexity, it could surpass it, evolving into forms of intelligence and sophistication we can hardly imagine. Even better, K218 itself is what astronomers call a quiet red dwarf. While many of its kind unleash violent stellar flares, releasing radiation strong enough to sterilize planets, K218 burns with unusual calm. This stability allows atmospheres to remain intact and ecosystems to thrive for eons. The Goldilocks zone. K218b orbits its star in just 33 days, hugging far closer than Earth does to the sun. Yet because K218 is cooler and dimmer, this tight orbit places the planet in the Goldilocks zone, a region where temperatures are just right for liquid water. This is no fleeting window of habitability. Unlike Earth, which will one day be consumed when our sun swells into a red giant, K218b could linger in this perfect zone for trillions of years. Life there has time beyond measure, time to expand, diversify, and advance in ways we can only dream about. And while the planet is tidally locked, one face bathed in eternal daylight, the other in endless night, the thick hydrogen atmosphere acts as a great equalizer, redistributing heat so that both hemispheres remain surprisingly stable. The result? A world of extremes, but not of death. Instead, it is a planet offering two permanent realms, a day side of unbroken sunlight and a night side of perpetual starlight, both brimming with unique opportunities for life. Asterisk. The 120 light-year journey, yet for all its promise, K218b is unimaginably far. Its light must travel 120 years across the abyss of space before touching the mirrors of our telescopes. When that light finally arrives, it carries the molecular fingerprints of an alien world. To put that distance in perspective, when the photons we now observe left K218b, Teddy Roosevelt was President of the United States. Earth was just stepping into the industrial age. Now, over a century later, those photons are telling us a story, the breath of alien life. Preserved in light, even from such a distance, the signals are unmistakable. The dimethyl sulfide detected in K218b's atmosphere isn't the whisper of a struggling biosphere. It is the roar of a thriving an entire planet's worth of biology, producing signatures powerful enough to be read across interstellar space. This distance turns K218b into a paradox, far beyond our reach for human exploration, yet tantalizingly close in astronomical terms. In a galaxy of over 100 billion stars, it sits within our local neighborhood. Close enough to study in detail, close enough to transform our understanding of life, close enough to remind us we are not alone. And soon, with the coming generation of telescopes, massive observatories with mirrors 100 feet across, we may detect not just one biosignature, but dozens. Each molecule a message. Each signal a revelation. K218b is not just another exoplanet. It is a window into the deep future of life, a reminder that while Earth may fade, the cosmos has worlds where life can thrive for trillions of years. The local galaxy and first contact. If life truly exists on K218b, then it reshapes how we see our place in the cosmos. It suggests that our own galactic neighborhood may be teeming with living worlds, each with their own unique ecosystems and evolutionary paths. And here's the most striking part. K218b is close enough that, if intelligent life exists there, they could be watching us right now. The very first radio signals that left Earth a century ago are only just now brushing past their star system. To them, our earliest broadcasts would arrive like a faint cosmic announcement: we are here. For the first time in history, the possibility of mutual detection feels less like science fiction and more like science fact, the coronagraph breakthrough. But how do we even glimpse a planet like K218b when its star outshines it by billions of times? It's like trying to photograph a firefly fluttering beside a searchlight from 1,000 miles away. That was the seemingly impossible challenge faced by the James Webb Space Telescope. The solution came from an unlikely source, our own sun. For decades, astronomers used devices called coronagraphs to block the blinding disk of the sun and reveal its faint outer atmosphere. Engineers adapted this same principle for Webb, but with technology far more advanced, Webb's coronagraph doesn't just block starlight, it sculpts it. Using a series of masks and mirrors, it creates a carefully engineered eclipse, snuffing out the star's glare while letting the faint glow of orbiting planets shine through. To succeed, Webb must maintain stability so precise it's like holding a laser steady enough to hit a dime on the moon. Any vibration, even a fraction of a hair's width, would blur the fragile signal, and even when the starlight is blocked, false signals, called speckles, still litter the image, mimicking planets. To overcome this, Webb relies on artificial intelligence, scanning the data like a cosmic detective. Imagine searching through millions of photographs at once, hunting for a single familiar face. That's what it takes to distinguish a real exoplanet from a trick of the optics. This marriage of precision engineering and machine intelligence has transformed the impossible into routine. With contrast ratios of 10 billion to 1, Webb can now spot a lone candle burning beside the brightest stadium lights on Earth, across interstellar space. Planetary habitability and the mass surprise. But perhaps the most astonishing revelation came not from Webb's images, but from the numbers themselves. When astronomers calculated the mass of K218b, they expected disappointment. At 8.6 times the mass of Earth, The planet seemed destined to be another gas giant like Saturn, a world of clouds with no solid surface, but the data told a different story. K218b isn't a gas giant. It appears to be a super-Earth water world, a planet where oceans could stretch for thousands of miles, and conditions might support life even more effectively than Earth itself. The planet's immense gravity, nearly 3 times stronger than Earth's, doesn't crush possibility, it protects it. That gravity locks in a thick atmosphere, shielding it from deadly solar flares. It prevents water from slowly bleeding into space. As it once did on Mars, it creates a world where oceans can accumulate and endure for billions, even trillions, of years. On Earth, we often think of our planet's size as just right for life. But K218b challenges that idea. Here, bigger truly can be better, forging a cradle for life that may outlast Earth itself by cosmic orders of magnitude, the ocean core of a super-Earth deep within K218b. The crushing pressures at its core likely prevent the formation of a solid iron heart like the one that anchors Earth. Instead, scientists believe its center may be composed of water ice, surrounded by colossal layers of liquid oceans stretching hundreds of miles deep. These vast global seas could dwarf every ocean on Earth combined, creating an almost unimaginable cradle for life to emerge, adapt, and flourish. But what makes K218b truly extraordinary is where it falls in the planetary spectrum. Astronomers classify it as a super-Earth, a world massive enough to hold on to thick atmospheres and deep oceans, yet not so large that it balloons into a gas giant like Jupiter or Saturn. This delicate balance between rocky stability and atmospheric richness may be one of the most crucial markers of habitability. And K218b sits precisely in that sweet spot. The advantage of mass? The planet's immense mass doesn't just shape its oceans and atmosphere, it also controls its long-term destiny. Larger planets retain their internal heat for far longer than smaller ones. On Earth, our core is slowly cooling, inching toward a future where our world will one day grow geologically silent. But K218b's sheer size grants it endurance on an almost cosmic scale. It may remain geologically active for trillions of years, longer than the current age of the universe itself. This internal activity could keep driving volcanic cycles, releasing gases, and maintaining a self-regulating carbon system that keeps the atmosphere stable. In essence, K218b isn't just habitable, it may be habitability perfected. A world more enduring, more stable, and perhaps more life-friendly than Earth. This realization has shifted the focus of planetary science. We're no longer searching for an Earth twin. We're searching for Earth's bigger, stronger, and longer-lived cousins. And in a galaxy where super-Earths are far more common than Earth-sized worlds, that may mean life is not a rare accident but a recurring theme. The hidden world of CE yet sometimes? The most groundbreaking discoveries come not from what we see, but from what we around a young star named CE. Webb detected something remarkable, not a planet directly, but a mysterious gap carved into the star's debris disk. These cosmic rings of dust and ice are the raw construction zones where planets are born. And when a gap appears, it's the calling card of a hidden world sweeping through, collecting and clearing material in its path. CE's disk, viewed face-on from Earth, revealed a breathtaking architecture, 3 concentric rings, each separated by distinct voids. Within one of those gaps, Webb's infrared vision detected a faint glow, evidence of a new planet forming. Exactly where computer simulations predicted it should be. This world, now identified as a Saturn-mass planet, isn't just drifting in its orbit. It is actively sculpting its stellar system, clearing debris on one side, while shepherding material into organized rings on the other. A planet shaping not just itself, but its entire cosmic neighborhood. A young world in the making. The planet's measured temperature, around 120 degrees Fahrenheit, places it tantalizingly within the habitable range, where liquid water could exist. Even more astonishing, its location inside the debris disk suggests it is still young, perhaps still accreting matter. In other words, we may be watching this world in its infancy, a baby planet in the earliest chapters of its story, a world that in billions of years might host seas, atmospheres, and perhaps even life of its own, a new era of discovery. These breakthroughs mark a turning point. With K218b, we glimpse a stable water world that could sustain life for trillions of years. With CE-Antel, we witness a planet being born in real time, sculpting its environment like an artist shaping clay. The message is clear: the universe is not static. It is alive with worlds, some fully formed, others just beginning, and perhaps countless others already thriving with life. We are not just discovering planets. We are witnessing an unfolding cosmic symphony, the birth, growth, and endurance of new worlds across the stars, a galaxy alive with possibilities. The galaxy is not merely sprinkled with a handful of habitable worlds. It is teeming with them, planets that could sustain life, each offering its own unique recipe of conditions and opportunities for biology to emerge. Within just a 200 light-year sphere around Earth, astronomers have already identified more than 50 worlds that show strong signs of habitability. These range from massive super-Earths like K218b, with oceans that dwarf our own, to smaller rocky planets nestled gently in the temperate zones of dim red dwarf stars. Each of these worlds is a natural experiment in planetary evolution, a unique combination of chemistry, climate, and energy that could give rise to life unlike anything we have ever known. A staggering diversity of worlds. The variety is staggering. Some planets orbit perilously close to their stars, where thick atmospheres generate powerful greenhouse effects, conditions so intense they can keep water liquid at temperatures hot enough to boil Earth's oceans away. Others drift in the far reaches of their systems, where frigid surfaces hide vast subsurface oceans warmed by geothermal energy and sealed beneath frozen crusts. These hidden seas could harbor entire ecosystems, thriving in eternal darkness. A few worlds are locked in perpetual ice, yet their inner warmth may still sustain life beneath their frozen exteriors. It is not just the number of habitable worlds that astonishes astronomers. It is their variety, an endless range of environments, each rewriting what habitable can mean. The role of stars in life's story. Different stars craft different stories of habitability. Red dwarf stars, making up nearly 3/4 of all stars in the galaxy, provide habitable zones that can last for trillions of years, giving life nearly limitless time to evolve, adapt, and grow in complexity. By contrast, larger and brighter stars burn hot and fast, creating shorter-lived habitable zones. On these worlds, life may be forced to evolve rapidly, adapting at breakneck speed before the star's energy burns out. Galactic census of life's potential. The implications are breathtaking. If our local neighborhood alone, just a small patch of space within 200 light years, already contains more than 50 potentially habitable planets, then by simple scaling, the Milky Way itself could contain billions of life-supporting worlds. Worlds not just like Earth, but stranger, harsher, perhaps even better suited for life in ways we are only beginning to imagine. The Milky Way, a galaxy of living worlds. The Milky Way, with its 400 billion stars, may harbor more living worlds than there are people on Earth. Each one is a unique answer to the universal challenge of sustaining life. Some may resemble Earth, evolving oxygen-rich atmospheres that support complex, multicellular organisms capable of breathing, moving, and even photosynthesizing. Others may have taken an entirely different path, with hydrogen-based biochemistries that fuel ecosystems unimaginable to us. And then there may be worlds whose evolutionary stories we have not yet even conceived. The implications for the search for extraterrestrial intelligence are staggering. If life emerges easily across the galaxy, then intelligent life may also be widespread. The radio telescopes straining to capture faint signals from alien civilizations might not have to wait long. In a galaxy filled with living worlds, the question is no longer whether intelligent life exists, but how many civilizations are out there, reaching back toward us. Perhaps most profoundly, the sheer number of habitable worlds suggests that life itself may be a fundamental feature of the universe. Just as stars form naturally from collapsing clouds of gas and dust, Perhaps life arises just as inevitably wherever conditions allow. If so, we are not isolated in a vast empty cosmos. We are part of a cosmic community of living worlds stretching across the entire galaxy. The universe may be far more alive than humanity ever dared to imagine. Yet this gap is not just an absence of matter, it is a story written in gravitational architecture. The sharp boundaries imply that the planet is not merely pushing material aside, but actively orchestrating it. Dust and debris that might otherwise orbit chaotically have been shepherded into well-defined rings, creating a structured, almost elegant design within the disk. Computer simulations confirm this intricate dance. The planet's gravity generates resonant safe zones where debris can accumulate without being consumed, matching precisely with the rings astronomers observe. Far from being a passive wanderer, this young planet is a cosmic architect, sculpting the blueprint of its stellar system. The gap also reveals secrets about the planet's past. Among the materials it has gathered are water-rich asteroids and icy comets, suggesting the world has acquired the volatile compounds essential for atmosphere building, and potentially for life. With a current surface temperature of roughly 120 degrees Fahrenheit, this planet seems to have retained enough of those ingredients to support a thick, life-friendly atmosphere. But the story grows deeper still. This recurring temperature 120 degrees emerges again and again across Webb's most promising discoveries, as if the cosmos itself has set the thermostat. This value represents a near-perfect equilibrium for life. At 120 degrees, liquid water thrives as a universal solvent, dissolving and transporting a wide array of nutrients. Chemical reactions proceed quickly enough to fuel metabolism, yet gently enough to preserve delicate molecular structures. On Earth, this temperature is mirrored in some of our most extreme habitats, deep-sea hydrothermal vents where life has evolved astonishing adaptations independent of sunlight, powered only by chemistry. Experiments here on Earth show that such conditions are also optimal for the synthesis of amino acids, the very building blocks of proteins. It is a temperature where chemistry does not merely survive, but flourishes, producing the foundations upon which biology can be built. Across the galaxy, planets maintain this life-favoring warmth in diverse ways. Some are heated by thick greenhouse atmospheres of hydrogen or carbon dioxide, trapping starlight with astonishing efficiency. Others are warmed from within, powered by radioactive decay or the slow crush of gravitational forces. In some, both mechanisms work in harmony, producing a stable cradle for potential life. The fact that worlds so different converge on the same temperature range suggests something profound. That 120 degrees Fahrenheit may not be a coincidence, but a universal optimum, a cosmic sweet spot where chemistry naturally organizes itself into the first steps of life, just as stars appear to favor certain masses and sizes that allow them to burn steadily. For billions of years, planets too may favor specific temperatures conditions where life can not only emerge, but flourish. One of these appears to be a narrow range around 120 degrees Fahrenheit. Far from being merely habitable, this warmth seems actively beneficial for biology. At this temperature, evolution itself may accelerate. Faster metabolic activity, increased mutation rates, and stable climates combine to create an environment where life does not just survive, but diversifies rapidly. Biospheres on such worlds could evolve with a richness and complexity exceeding anything seen on Earth. The repeated discovery of planets resting in this thermal sweet spot hints at something profound. The universe may not simply allow life, it may encourage it. The balance is too perfect to dismiss as chance. The 120-degree optimum may be the cosmic signature of inevitability, a sign that biology is written into the very structure of the universe. But temperature is not the only clue. On a distant planet named K218b, the James Webb Space Telescope detected something even more startling: methane. This simple molecule, one carbon atom, bound to 4 hydrogen atoms, should not exist in such abundance. Methane is fragile, easily broken apart by ultraviolet radiation from a nearby star. Its persistence in K218b's atmosphere implies that something is replenishing it constantly. on Earth that something is life, from swamp-dwelling microbes, to the digestive systems of animals, to subtle processes within plants. Virtually every major methane source on our planet is biological. Geological sources alone cannot sustain methane at detectable levels, which raises the question, if not biology, then what is keeping methane alive on K218b? The levels Webb has uncovered are staggering orders of magnitude higher than what geology alone could provide. Such concentrations suggest a planet where life is not marginal or struggling, but thriving, so active, in fact, that it is reshaping atmospheric chemistry on a planetary scale. And yet the mystery deepens. Methane's role in K218b's hydrogen-rich atmosphere may go far beyond what it plays on Earth. Here, methane could serve as both fuel and framework, a source of carbon, a source of energy, and a building block of organic molecules. In laboratory experiments, mixtures of methane and hydrogen under the right conditions have produced amino acids, the very foundations of proteins. On K218b, this chemistry could be occurring on a planetary scale, turning the atmosphere into a giant biochemical factory. This methane signature also tells us something about the planet's history. It suggests that K218b has sustained active biological processes for immense spans of time, millions, perhaps billions of years. Its climate and atmospheric chemistry have remained stable enough to support evolutionary progress, allowing complexity to deepen generation after generation. Perhaps most remarkably, methane may be only one voice in a far larger symphony. The planet's skies contain a dynamic blend of gases, each interacting in ways that could support multiple forms of metabolism. Entire ecosystems may stretch not across land or ocean, but through layers of atmosphere, creating a biosphere that breathes and evolves as a single living system. This is not just a puzzle of chemistry, it is evidence of a world alive. A planet where biology and atmosphere have co-evolved into a self-sustaining engine of complexity, unlike anything Earth has ever witnessed, and this discovery is only the beginning, with Webb's instruments now capable of detecting such biosignatures. Across interstellar distances, astronomers are preparing for the next great survey, an unprecedented campaign that could reveal dozens of living worlds orbiting nearby stars within the coming decade. For the first time in human history, we stand on the threshold of charting not just where life could exist, but where life does exist. The next great phase of exploration will focus on what astronomers call the Biosignature Survey, a systematic search for the chemical fingerprints of life in the atmospheres of planets orbiting nearby stars. This ambitious campaign will target more than 200 star systems within just 100 light-years of Earth, analyzing the air of every potentially habitable world that can be observed. The goal is nothing less than historic: the creation of the first comprehensive catalog of life in our cosmic neighborhood. The James Webb Space Telescope, armed with new observing modes, will soon push beyond its current limits. No longer restricted to planets that conveniently transit their stars from Earth's perspective, Webb will be able to study worlds that orbit at angles previously hidden from view, vastly expanding the sample size of planets under investigation. To make sense of the torrent of data, advanced algorithms will search for complex molecular combinations, patterns that could indicate not just life as we know it, but life based on alternative biochemistry. And for the first time, time series observations will track the way atmospheres change across months and years. Just as Earth's air reveals seasonal variations caused by biology, similar cycles on alien planets could reveal living worlds in motion, ecosystems responding to stellar rhythms and planetary seasons. But the search will not end with biology. Astronomers will also begin looking for technosignatures, the atmospheric scars of industry, the chemical byproducts of technology itself. Artificial pollutants, detectable across interstellar distances, would be unmistakable evidence of advanced civilizations. This search will be global and multifaceted. Radio telescopes will listen for signals from star systems where Webb detects promising biosignatures. Optical telescopes will hunt for subtle glow signs of artificial lighting on the night sides of alien worlds. Together, these instruments will form the most comprehensive search for life and intelligence ever attempted. Future advances already on the horizon will sharpen the view even further. Improved coronagraphs will allow astronomers to directly image smaller, more Earth-like planets. Next-generation spectrographs will dissect their atmospheres in exquisite detail. And new image processing techniques will extract faint signals, buried deep in the data, revealing biosignatures that today remain invisible. And this is only the beginning. The breakthroughs made by Webb mark the dawn of a golden age in the exploration of extraterrestrial life. Over the next 2 decades, an entire fleet of planned observatories and advancing technologies promises to transform our ability to detect and study life on distant planets, revealing a universe that may be far more biologically rich than we ever imagined. At the forefront of this future stands the Habitable Worlds Observatory, a visionary space telescope designed specifically to seek out Earth-like planets orbiting Sun-like stars. Equipped with advanced coronagraph technology, it will achieve contrast ratios of 10 billion to 1, allowing astronomers to directly image Earth's true analogs. For the first time, we will be able to probe their atmospheres in detail, searching for water vapor, oxygen, and the molecular fingerprints of biology itself, but the effort extends beyond space. On the ground, engineering marvels are also taking shape. The extremely large telescope, now under construction in Chile, will boast a mirror more than 100 feet across, 5 times larger than Webb's. This vast eye on the sky will scrutinize the atmospheres of nearby exoplanets with unprecedented precision, detecting dozens of molecular species that could serve as beacons of life. Yet the search for life is not simply a matter of building bigger telescopes. Artificial intelligence and machine learning are being developed to handle the enormous torrents of data these instruments will generate. These tools will recognize faint patterns in atmospheric chemistry that human observers might overlook, patterns that could betray life forms based on entirely different biochemistry from our own. Scientists are also pioneering the concept of agnostic biosignatures, chemical fingerprints that signal life without assuming Earth-like biology. Rather than searching only for oxygen or methane, these methods will look for chemical imbalances that cannot persist without the active hand of biology. In this way, we may detect forms of life utterly unlike anything we know. Even more extraordinary is the prospect of watching alien worlds breathe in real time. The next generation of observatories could monitor changes in planetary atmospheres over days and even hours, capturing the daily rhythms of entire biospheres as they respond to sunlight, rotation, and the changing seasons of alien worlds. And then, the boldest possibility of all, detecting technological civilizations. Future telescopes may be sensitive enough to detect atmospheric pollution from industry, the glow of artificial lighting on a planet's night side, or other unmistakable signs of intelligent activity. The search for extraterrestrial intelligence will shift from speculation to systematic science, woven directly into the study of exoplanets themselves. Within just 2 decades, humanity may have identified not a handful, but hundreds of living worlds, each with its own atmospheric chemistry, its own ecological history, its own story of evolution. The evidence may soon reveal a profound truth that the universe is not merely habitable. It is abundantly alive, with biological processes unfolding on scales that dwarf anything in Earth's history. The search for life beyond our world is converging on an answer to humanity's oldest question: are we alone? The evidence now suggests the answer is a resounding no. And soon we may discover just how much company we truly have. The moment itself will arrive quietly, not with fireworks or headlines, but with a scientist staring at a computer screen examining data returned from the James Webb Space Telescope. In that instant, humanity's cosmic solitude will end forever. The signal will be undeniable, a pattern of atmospheric signatures that can only be explained by life actively transforming the chemistry of an entire planet. Already, the discovery of life on K218b has brought us to the edge of this epochal moment. With 99.7% statistical confidence, Webb has revealed the chemical signatures of biological activity 120 light-years away. Dimethyl sulfide, a molecule produced only by living organisms on Earth, has been detected in its atmosphere. The interplay of methane and hydrogen, combined with a chemical disequilibrium that cannot persist without ongoing biology, points unmistakably to a living world. But absolute certainty awaits. Independent observations will confirm these biosignatures. Competing explanations will be ruled out one by one. Confidence levels will rise from 99.7% to 99.99% until there is no reasonable doubt. When that moment comes, everything will change. The implications will reverberate across every aspect of human life. Science will be revolutionized, no longer confined to the assumption that Earth is a singular biological oasis. Philosophy and religion will be transformed as we confront the reality of other living worlds. Technology will accelerate as we develop new ways to study and perhaps someday communicate with alien ecosystems. And psychologically, the discovery will end the loneliness that has haunted us since the first humans gazed into the night sky and wondered if anyone was looking back. We will understand ourselves not as isolated beings, but as members of a galactic community of living worlds, each shaped by its own evolutionary history, yet all sharing the same universal spark. But with this revelation will come responsibility. As we uncover more living planets, humanity will face profound ethical questions. Do we have obligations to protect and preserve life beyond Earth? What role must we play as a spacefaring civilization within a galaxy alive with possibility? The day we are no longer alone will mark the beginning of a new chapter in human history. We will transition from a species that speculates about extraterrestrial life to a civilization that knows it exists, and thrives throughout the stars. The universe will no longer appear as a silent, empty void, but as a vast ecological tapestry, rich with biology and endless experimentation. Looking back, history will remember Webb's detection of biosignatures on K218b as the turning point. The first step in our journey from cosmic isolation to galactic citizenship. The faint chemical whispers of dimethyl sulfide carried across 120 light-years of space will be remembered as the signal that ended humanity's loneliness. The moment of discovery is almost here. Everything is about to change? For in the atmosphere of a distant world, wrapped in hydrogen clouds and warmed to a gentle 120 degrees Fahrenheit, life is breathing. And for the first time in history, we are close enough to hear it. But K218 billion is not alone. The James Webb Space Telescope has unveiled a universe where potentially habitable worlds are not rare exceptions, but part of a cosmic abundance, each offering its own unique stage for life to emerge and thrive. From the swirling debris disks around newborn stars where planets are still taking shape, to the ancient glow of red dwarfs destined to burn for trillions of years, the galaxy is filled with environments where biology is not just possible, but perhaps inevitable. The implications reach far beyond astronomy. What we are witnessing is the end of humanity's cosmic loneliness, and the beginning of our recognition as citizens of a galactic community. The universe is not a cold void punctuated by rare sparks of life. It is a living ecosystem, operating on scales that dwarf anything Earth has ever known. And this is only the beginning. The instruments that made these discoveries possible are the first step. Future observatories will allow us to read the atmospheric signatures of hundreds of living worlds, each with its own biochemistry, each shaped by its own evolutionary history. We may one day encounter life that shares nothing with Earth's biology, life based on chemistries we have never imagined, expanding our understanding of what life can be and how it arises. The moment we confirm beyond doubt that we are not alone will mark a turning point in civilization itself. Every child born after that day will grow up knowing that life exists across the stars, that humanity belongs not to a single world, but to a galactic community. The philosophical and spiritual reverberations will touch every culture, every belief, every sense of identity. But perhaps the most profound realization is this: life is not an anomaly. It is the universe's natural tendency. Wherever conditions permit, life takes hold. It grows, it transforms entire worlds. The chemical whispers detected by Webb are not merely signals of alien organisms. They are evidence that the universe itself is fundamentally alive. For the first time in history, we can see our true cosmic neighborhood. And it is not barren, it is vibrant. We are not alone, and we never were. The universe has been waiting for us to open our eyes, to build the tools capable of perceiving what has always been there, a cosmos teeming with life, breathing with the rhythm of countless biospheres, alive with possibilities we are only beginning to imagine. The universe is alive, and we are part of its unfolding story.